This video gives an introduction to the P and NP complexity classes using the Clique problem as an example. You should know about asymptotic notation and graphs and maybe just algorithms in general before watching this. A complete graph is an undirected graph with all of the edges. If it has 0, 1, or 2 vertices, that doesn't tell you much, but once we get to bigger graphs, we can see the structure. If that complete graph is a subgraph of another graph, it's called a clique or a clique, like a bunch of kids who all hang out together with less drama. When our size 6 clique is hidden within a larger graph, it's harder to spot. But if somebody tells you that some set of vertices in the graph is a clique, it's easy to verify. You can go through each pair of vertices in the set to check that there's an edge between them. If it is a clique, we get through the entire set and verify it. If somebody gives us a set that isn't a clique, when we get to a pair of vertices that has no edge, we figure out it isn't a clique. How long that takes might depend on what format the graph is in, but it shouldn't take more than v squared time, so polynomial in the size of the input. That brings us to the complexity class P for polynomial. Problems fall into the P complexity class if they are decision problems, yes-no problems, that can be solved in polynomial time. Asymptotic notation ignores constant multipliers, so you can give a set of all problems that can be solved in, let's say, n squared runtime, regardless of the coefficient. This goes further, ignoring constant exponents, so it catches all polynomials of any fixed degree. Roughly speaking, for real-world problems that come up, if we can find a polynomial time algorithm to solve them, the thought is that those problems can be solved efficiently. Of course, n to the 100th algorithms are polynomial, but not efficient, but those don't come up so much. Because we can solve the clique verification problem in polynomial time, and it's a decision problem, it is in P. The problem gets harder if we're just given a graph and asked if it has a clique of a given size, without being told what the clique is. We could just check each possible subset of the right size. If we fix the size and ask how the runtime of that changes as the graph grows, it's polynomial, though for large sizes, not very practical. But if we let the size also grow with the runtime, it isn't polynomial. That's not a problem for our tiny graph here, but if you want to check all size 25 subsets in a small graph with 50 vertices, there are a lot of possible subsets. You're not going to want to wait for it. Hold on. This problem is in a complexity class called NP for non-deterministic polynomial. That name comes from the original way the class was defined, but we'll use a different definition here that defines the same class. A problem is in NP if it is a decision problem, and for yes instances there's a certificate or a proof that somebody can give you to help you verify that it's a yes instance in polynomial time. The clique problem is in NP. We already saw that if somebody gives you the clique itself as a certificate, you can verify that it's a clique, but we don't know of any polynomial time algorithms to solve clique. For instances with a no answer, you don't need a proof, but your verifying algorithm can't ever be tricked into verifying that a no instance is a yes instance. If you have a decision problem where negative instances have proofs that can be verified in polynomial time, but you don't need a proof for yes instances, those problems are in the complexity class co-NP. Their complement is in NP. So for sure, P is a subset of NP and co-NP. For problems in P, instances don't need any certificate. In polynomial time, solve any instance, and that verifies that it has a yes or no answer. Also, remember that saying a problem is in NP doesn't imply that it's hard. It's a statement of ease. It is a limit on how hard the problem is, but the problem might still be very easy. Everything in P is also in NP. It'd be like if I told you that as a professor, I make less than $1 billion per year. that gives an upper limit on my salary. It's a high limit, but maybe I don't even make half that amount. Of course, lots of times we're interested in optimization problems, not decision problems. But if you had a way to efficiently solve the decision problem, you might be able to use that to solve the optimization problem. Let's consider the clique problem. Suppose that you had a polynomial time black box that could solve the decision version. Can that help you to solve any optimization problem? A simple optimization version might ask, what's the size of the largest clique in a graph? You could use the black box in a binary search to find the largest size, or you could just be lazy and do a linear search. Either way, you run the polynomial time black box a polynomial number of times, so it takes polynomial time to answer. But what if you want to actually find a maximum sized clique? Well, first find what the size of the largest clique is. It's 6 here. Next, you can go through your vertices one at a time to see if they're needed to make a clique of that size. So maybe I make a new graph with the first vertex removed, and I ask if there's still a clique of that maximum size in the new graph. In this case, there isn't. So I made a mistake. That first vertex is needed in my clique. I go back to the previous graph, marking that the first vertex is definitely in the clique, and then I try removing the second vertex next. The black box tells me that there is still a clique of size 6 without that vertex. There might also be a size 6 clique that includes vertex 2, but whether or not there is one, we know there's one without it. Let's find one of those. We permanently exile vertex 2 and continue on. We temporarily delete vertices, and if the resulting graph still has a clique of the maximum size, we make that deletion permanent. Otherwise, we bring the vertex and its edges back into the graph, marking that it will be in our clique. When we keep 11, we now have 6 vertices marked. They must form a size 6 clique. But we could also just continue with the algorithm, which will tell us to toss vertex 12. We end up running that black box a linear number of times, and it takes polynomial time each. So that gives a slightly larger polynomial time algorithm to solve the optimization problem. There are lots of open questions about complexity classes, and the granddaddy of them all is whether or not P is equal to NP. I think the general consensus is that it isn't, but that hasn't been proved. If they aren't equal, there are still other related questions that might still need to be answered, like whether or not NP equals co-NP. And if they aren't equal, does P equal their intersection? The next video covers related classes that are statements of difficulty instead of a statement of ease. Anyway, that's it for this one. I've got to go freeze some warts off.